Okay, hi guys. We are back with probability with respect to this particular topic called discrete probability distribution. Okay, that's what we are going to look at. Discrete probability distribution. This is in a series of probability lecture videos. This is what I'm taking to be part 3 of probability lecture videos. What can we associate to discrete probability distribution? In short, we can explain or express discrete probability distribution in this manner. For instance, here I've said that given x as a variable, then we assume that x can assume a definite set of values in the nature of x1, x2 through to xn with respect to probabilities p1, p2 through to pn, where p1, p2, p1 plus p2 plus p through to pn is always equal to 1, because we know that the sum of probability always totals 1. Okay. In this particular case, we can say that a discrete probability distribution for x has been defined. If we set in that manner, we can say a discrete probability distribution for x has been defined. Now, with this definition, it brings us closer to start looking at some of these functions. So when you talk about functions in terms of probability function, we can write a mathematical statement which is reading p open bracket x, which simply means it's a probability of x as a function with respect to values of p1, p2 through to pn for x, which can take the values of x1, x2, xn, meaning that there's a variation of values in that particular respect. So if we line them up in that manner, then and state them in that manner, that can be called a probability function of x. A probability function of x. Now, since x assumes certain values within given probability, as we have seen, it is often called a discrete random variable. Discrete random variable, okay, or a chance variable. In some other probability literature, you find it being called stochastic variable. So those are interchangeably used, and they mean one and the same thing, as I've explained. Okay, let's look at an example to demonstrate this discrete probability distribution. We make use of this example, which states that let a pair of a fair dice be tossed and let x represent the sum of points obtained, and then the distribution can be obtained in the following manner, in which I'm going to show you. So a fair die is that which is not biased. Okay, so when you look at a die, there are 6 facets, ranging from one face which has one dot through to a face which has 6 dots. So that's what we find on a die. Okay, so a fair one is one which is not biased, meaning that every side has an equal chance of turning up when you toss a die. Then we call that die a fair die. So let's look at that which we have talked about. As I've said, if you toss 2 fair die, a pair means that 2, we have one which is represented here on the as a column, the first column, and the other one which is taking the first row there. So there are chances that when you throw or toss a pair of this fair die, you can have a chance that one has one die has one turning up, and the other one also has one turning up. So the sum would be 1 plus 1, which is going to be 2. Okay, which is going to be 2. Let me just look this one. Okay, so we have here 1 and 1, so the sum is 2. Suppose you have on one die 1 faces up, on the other one 2 faces up, then you are going to have 1 plus 2, which is 3. So suppose you have on first die 1 turning up, on the second die 3 turning up, then you are going to have the sum 3 plus 1, which is equal to 4. So it is possible also to have 2 turning up on the first die and 2 turning up in the second die, then you have 2 plus 2, which is 4. So these figures, which are not in bold, are showing the summation of the outcomes of the 2 die tossed. Okay, so these are the possible outcomes: 2, 3, 4, 5, 6, and so on and so forth. So these are the possible outcomes in this particular table presented. Now, if we look at that, we can actually determine the chance that in this particular case, the second table, the chance that a 2 turns up. What is the probability that when you toss a die, the sum will be 2? So look at this one. There's only 1 here. How many are these possible outcomes? There's 1, 2, 3, 4, 5, 6, and also 1, 2, 3, 4, 5, 6. So the total number of possible outcomes is 36. So 36, if you count all these boxes here, there are 36 outcomes. So now, how many 2s do we see? There is only 1 out of the possible 36. So the probability will be 1 out of 36. So that's why you see in this particular box, the probability that you have a 2 as a sum after a pair of die is thrown is 1 out of 36. That's a probability. What's the probability that you're going to have 3 as a sum? You come here, you only have 2 possible outcomes. That is where you have the first one 2, then the second one 1. Okay, or where you have the first one 1 and the second one 2. So this will give it 3 as a sum. So there are 2 3s out of the possible 36 here. So the probability is 2 out of 36. So that's what you are going to see here. The chance that you obtain a 3 is 2 out of 6. Equally, when you look at the chance that you have a total of 4, you look at this table. How many 4s do we have? There are 1, 2, 3. There are 3 4s, means that 3 out of possible 36. So the probability is 3 out of 36. The chance that you have 5, it will be how many 5 do you have? 1, 2, 3, 4. 4 5s out of the possible 36 outcomes. So it will be 4 out of 36. It goes on until you get probability of getting a 7 is 6 out of the 6. Probability of getting an 8 sum will be 5 out of the 6 until it comes down to probability of getting a 12. That will be again 1 out of 36. 1 out of 36. So that's what it is. Okay, so this is what is presented as a probability distribution table. Okay, you have here. Okay, so now we have this table of these probability functions of x. So now we look at how do we present this in diagrammatical form or in a chart form. So we come here, look at this one. Okay, so this probability, if you are to chart them, the probability that you get 2 will be, as we have seen, is 1 out of 36, which is in decimal form is somewhere here. Probability that you have a 3 is 2 out of 36, which is somewhere here, and goes on like that. The highest is the probability that you have a 7, which is here as given as 6 out of 36. which is the highest. So it will come here. If you put this 6 divided by 36, it will come to be, if you read it along the y-axis, it will give you that. Okay, then after that it starts dropping, so it can be shown in form of a bar chart in this manner. So that's the probability distribution chart. That's the probability distribution chart. We have the probability distribution table, then you have probability distribution chart for the same data which has been evaluated from that. Okay, so now once that is done, what can we say about factors? This is similar to a relative frequency distribution with the relative frequency substituting probability. That's what we saw when we looked at probability part 1. We talked about relative frequency distribution of frequency tables. If you are not so sure, please go back to my YouTube channel, probability part 1. You get this particular explanation. Then, assuming the number of observations is very large, then the probability distribution can be said to be theoretical or limiting form of relative distribution. Again, in this particular case, we are talking about probability distribution can be taken to be that of population, whereas relative frequency distribution are sample distribution drawn for population. So that's what we have. Okay, so that's what I wanted to show you, particularly about discrete probabilities. Discrete probabilities. So thank you for watching my video. Please don't forget to subscribe to my YouTube channel, and if you're happy with my presentation, please don't forget to like my video as well. Thank you so much. Until next time, goodbye.